Hi guys, I'm Geet Mankar. I recently graduated from IISER Pune. First of all, I'd like to thank my collaborators, Suman Sarkar, Biswajit Pandey, and Subha Majumdar, and also the organizers for giving me this opportunity. Okay, so I'll be talking about validating the cosmological principle. So let's get to what the cosmological principle is. I'll just briefly go over it. The isotropy and homogeneity of the universe at sufficiently large scales. This principle is very important for the lambda CDM model. It is supported by many observations such as the isotropy of the CMB, deep galaxy counts in different directions, and large scale galaxy surveys, and there are many more uh, tests of homogeneity and isotropy using these galaxy surveys. But recently there have been some claims made against it. So let's look at them. There's the KBC void, which is a very large void and can cause a 6 sigma tension with the lambda CDM model. There's a large quasar group, which is of a size more than what we would expect in a homogeneous and isotropic universe. There's again a giant arc. There are bulk flows, and there's dipole anisotropy, which is inconsistent with the dipole anisotropy of the CMB. Okay, so first I'll describe the data set I'll use for this. The data set will be the million quasars catalog. It has around 1.5 million galaxies, half of which are type 1 QSOs, around half of which have a 60% probability or greater of being quasars. Okay. Due to this survey being very non-uniform due to the galaxy and other stuff, we'll actually have to choose a region which is dense enough for doing this analysis. So we choose this region and a particular redshift range for our data set. These are the details. So the important part is that the radial co-moving length and the volume and the area are large enough so that we can actually draw inferences about cosmology from these. These are not very small length scales. Again, to compare with our what I'll get to later, we'll actually use mock data sets, one of which is homogeneous and isotropic, and the other is, for shorthand, I call it replica. It just mimics the radial distribution, the redshift distribution of the actual data set that we are using. Okay. Why Shannon entropy? So this is the formula, just the form of Shannon entropy. Shannon entropy is maximum for uniform distributions, and as the distribution gets clumped or clustered, the Shannon entropy decreases. So we actually have a maximum value for the Shannon entropy when the distribution is uniform, which we can use then to scale with the Shannon entropy of our data, so that we get a value between 0 and 1, right? This is very convenient. Okay, so before I get to the actual part, analysis part, what are the salient features of our analysis? Usually papers actually assume the Copernican principle for doing analysis about isotropy. We do not. Anisotropy is, so using different measures for the same data set or different data set may lead to biased results due to intrinsic biases in the measures or the intrinsic biases in the data sets. Again, so we need to actually do use the same measure on the same data set to actually be consistent for both inhomogeneity and anisotropy. Again, and anisotropies may also exist across the sky in one direction, and in another direction, the measure of anisotropy may actually be different. So we also need to check the transverse direction. Okay, we also look at KL divergences to actually check with if the measures are actually consistent with KL divergences too. Okay, what is the methodology? So I'll go back to the Shannon entropy part. So I told you that there's a maximum value. I scale the entropy of the data with the maximum value. And I just, so we get a value between 0 and 1. And I just do 1 minus that ratio. So I can actually call it inhomogeneity. So inhomogeneity of 1 means it is actually, everything is clustered at 1 point. And of 0 means it's completely homogeneous. Okay. Again, this is the form. Similarly, for anisotropy, we can, okay, before that, how will we actually do this? So we have our data set. We'll divide it into small 3D blocks. And then for each block, we have a specific number of data points in it. So we can get the probability of a data point being in that specific box. And we have a lot of such boxes. We calculate the entropy for each of these voxels, and then we add them up for a specific size of voxel, and then we increase the size of the voxels. So we get this inhomogeneity parameter as a function of voxel size, right? Similarly, for anisotropy, we actually use a redshift bin. So what we will start from is a redshift of 2.2. We'll make a bin, let's say, for example, from 2.2 to 2.3. We project it onto the sky. We pixelize it, and again do the same thing we did with the homogeneity parameter. Then we again project from 2.2 to 2.4, then 2.2 to 2.5. We so that we get a radial distribution for this anisotropy parameter. Again, we can also do this for the transverse case. If you have any questions later, I can address this after this. This is just the KL divergence. It essentially measures the distance between two probability distributions. So we made probability distributions for our inhomogeneity and anisotropy cases. This we can directly compare these two probability distributions using the KL divergence. Okay. Let's get to the results. So here we see Millikas is in red. We actually see the inhomogeneity parameter dropping very quickly as we increase the size of the voxels. What we are interested in where this inhomogeneity parameter flattens. We can see about at 250 megaparsecs is where the slope goes to 0. So we've reached a stabilization point, kind of. Similarly, in the KL divergence, we also see that the comparisons between the homogeneous mock and the replica mocks actually are very low. So 250 megaparsecs is around what we expect homogeneity to manifest at. Now getting to the anisotropy, we see the same thing, a sharp drop. The slope actually reaches 0 at 250 megaparsecs. Again, the KL divergences are very low for these two comparisons that we make. Okay. Similarly, for the transverse case, the thing with the pixelization was that we could not actually make many granular pixels. So we have only 3 data points here. We cannot say much about this here. We can only say that there's a drop in the transverse direction too. So summarizing, we see inhomogeneity in MOX and Millikas data get very close beyond 250 megaparsecs. Similar trend is visible in the KL divergences. So since these mock catalogs are actually randomly generated, these are not simulations, lambda CDM simulations. The only difference would be gravitational clustering. Again, for the anisotropy, we see a similar thing. for both inhomogeneity and anisotropy, the differences between these mocks and the data are of the order of 10 raised to -3. That's important. So summarizing my talk, we employed Shannon entropy to measure inhomogeneity and anisotropy as a function of voxel size and radius respectively. We see that around 250 megaparsecs is where homogeneity and isotropy manifest themselves. The KL divergence also agrees with the same. The differences between the data and the mocks are of the order of 10 raised to -3. If there are any large structures present within the data set, these do not pose a very big challenge to our analysis. Thank you. If there are any questions. Thank you.
Questions?
Thank you. This sounds super cool, but I'm a bit confused.
Yeah.
Can you help me? So Shannon he talks about the information carrying content of, say, the English language,
right,
in terms of the frequency of the different letters, right? Those are his probabilities of the frequency of the letter A, the letter B, and so on. A bit more complicated, but basically that. So in your case, what are the letters and what's the alphabet?
I'll get back to the. There's no help here. So we have a 3D distribution of points, right? We divide it into voxels.
Okay.
So, yeah.
Do these voxels contain a lot of particles, or either
Yes.
0 or 1?
No, they contain a lot of particles.
Okay.
So now we can get a probability that what is the probability of getting a data point in this voxel, is this one particular voxel, right? So the number of particles in this box divided by the number of particles in the whole region.
The letters of the alphabet are just occupation numbers.
Right.
How many? Okay.
Yeah.
Thank you. Now I need to think about it.
Does the bias of your sample have any role to play in this? Ravi was mentioning in his talk, like, what you're looking at should not come from a uniform sample. There should be, the more biased it is, the more clustered.
Can you explain a little bit more?
So if your quasars are more biased, they will also be inherently more clustered.
Right.
Right. Does that play a role in your analysis?
It does, but what we see from the analysis is actually they might have a very small effect. So going to the results, there's still a difference here, right? So that is actually because of the clustering and the bias in the distribution itself.
Right. So in principle, you can measure the bias assuming a cosmology from that.
Right.
Last question.
So I did not fully understand how you account for like observational effects. Like, are you trying to select a uniform distribution of quasars in some way? Or?
Not a uniform distribution, but it should be dense enough, and it should also be, so like there are not biases. When they actually survey the sky, you can actually see, let me back. So it's not visible here, but there's a region which is like, which goes like this. So that I exclude because it is clearly a limitation of the survey.
No, but I'm talking about in the redshift direction, right? Because you will see that the number density of these quasars will also change as a function of. So you try to account for that
in the replica form. Yes.
So let's thank the speaker again.